Yeah.
Number 6.
6, you got it. Oops. Number 6. All right, so our perfect squares, starting with 4. So the nice thing is, this happens to be a perfect square. Now, here's a question. Are each of these perfect squares? Yeah, why? They're even exponents. Good. So square root of 25 is 5. What's the square root of x to the second? X. What's the square root of y to the sixth? Y cubed. Oh, good terminology. I like it. Cool. And it's done. Where did the radical sign do? We did all the operation.
Can you also do number 15?
Yeah. Is that good here? 15. 2, 8. Oh, I can make an 8 better than that. 8x to the fourth times 5, 2x to the third. Okay, so on this one, we're going to look at it, and let's list a few perfect squares. 1, 4, 9, 16, 25, 36. Probably don't have to go any further. All right, so as of right now, I'm going to multiply the 2 and the 5 together to get 10. Now, does it make sense on this one for me to multiply the 8 and the 2 together, or should I just break them apart? Why? You're absolutely right, but why? 2 won't break apart. I like it. And 8 times 2 is what? 16, which is a perfect square, right? Okay, so right now underneath here, I'm going to get 16. Now, let's carefully think about this. How many total x's will be under the radical sign? 7, but 7's not even. So what should I do with my x's? So right now, these right now, there's x to the 7. So what do you think?
X to the 6 and x.
X to the 6 and x. Very good. Okay, that's still 7, or x to the 7th underneath. All right. Square root of 16 is how much? 4. So 10 times 4. Square root of x to the 6th? X to the 3rd. And then what's left under the radical? X. And then multiply outside. So 4 times 10 is 40. And we're done. Okay? Does that make sense? What else can I help you with? Yeah.
16.
Yeah. 16 is just a Pythagorean theorem problem, so we're eventually going to make this equation work. It says you have a 10-foot ladder. So you have like a wall sitting there, and you have a 10-foot ladder leaning against the wall. So that technically makes a right angle. Okay? How far from the bottom of the ladder from the wall when the ladder reaches 8 feet tall? So the distance, so because this is leaning against the wall, it's not going up all 10 feet, but this is 8. So we're going to call this A or X or something. I don't know. We can call it X if we want. And then, so my two shorter sides are the X and the 8. So I'm going to have X squared plus 8 squared is equal to 10 squared. So X squared plus 64 is equal to 100. And then I would subtract 64 from both sides. Those cancel. So X squared equals 36. And what should I do to both sides to get it just to be X? Square root. So X equals 6. That all right? I forgot who asked about that one. You. Anything else? Yeah. 14. You got it, bub. Number 14. So I have root 6xy squared. The other squared in that. Times 3x squared y squared. Okay. I'm just going to list off to the side some of my perfect squares. So I have 4, 9, 16, 25. That should be far enough. So, what should we do first? I guess we could multiply the 6 and the 3 together to get 18. But 18 falls about right here, right? So which perfect square times another number would give me 18 as well? 9 and 2, good. Do you see that? So yeah, I agree. 6 times 3 is indeed 18. But if you realize it's 18, then you could break it down to two other factors where one of them is perfect square. As far as my x's go, should I leave it just like that or should I combine them together? Leave it because the x squared is a perfect square, correct? And as far as the y's go, should I just put them together? Yes, I get y to the 4th. Does that seem to make sense? All right, so now we're ready to start doing the square root of stuff. What's the square root of 9? 3. What's the square root of x squared? X. And what's the square root of y to the 4th? Y to the 2nd. And then what do I have left underneath the radical sign? 2 and an x. Right. Done. Anything else I could help you with? Yeah.
Can you do number 11?
Yeah. Can I move out of the screen, guys? Number 11, I have root 72, x to the 3rd, y to the 4th. Let's list some perfect squares. Hey, why am I not listing 1 as a perfect square? Yeah, I don't need to. I mean, if you list it, it's fine, but 1 times whatever the number is going to work, but we're not worried about that. So 1, 4, 9, 16, 25, 36, 49, 64, 81. That should be enough. All right, so 72 falls about there. So we start from the bottom. Does the 64 times the number work for 72? No. Does the 49 times the number work for 72? What about the 36? Yeah, 36 times what? 2. What should I break x to the 3rd to? X to the 2nd and x. Is that okay? Do I break y to the 4th up? No, let's keep it as is because it's raised to an even exponent, so it's going to work. All right, square root of 36. 6 square root of x squared. Square root of y to the 4th. What do I have left behind? 2x. Done. How are you feeling about this, friends? Seem okay? I mean, you're responding to it nicely. So I either taught it really well or you're really smart. I think it's you're really smart because I'm not that good of a teacher. Any others I can help you with? Do you feel comfortable? Yeah. 12. You got it. So I get 7, 12, x to the 6th, y to the 4th. All right, so let's list a couple perfect squares over here. That's probably far enough. Okay, so 12 falls about here. So which of the perfect squares above that would multiply together to give me 12? 4 and 3, right? Do I need to break the x to the 6th or the y to the 4th down, or should I just leave them? They're both raised to even power, so I'm going to leave them. Okay? All right, so square root of 4 is 2, and notice I have it with the 7. The 7 was already outside. Okay, 3 is not a perfect square, so we'll leave that. Square root of x to the 6th. X to the 3rd. Square root of y to the 4th. Good. What's left behind?
4.
No.
Or
3. All right, take care of the multiplication outside. So 7 times 2 is 14. Done. Anything else, my friends? Hey, okay? Everybody happy? Yes, sir.
Number 13, please.
13, you got it. Number 13, root x y to the 5th times root 2y to the 3rd. All right, so let's list some perfect squares over here. 1, 4, 9, 16, 25, 36. I don't know how much we need. All right, so my friends, would it make sense to combine the 8 and the 2 together right now? Bless you. I think it'd be okay because that's going to give me 16, and 16's perfect square. And then what about the y's? Should I combine them together? Yeah. If I combine them together, how many y's do I get? Yeah, to the 8th. So as they were to the 5th and to the 3rd, which means they wouldn't have broken up. It weren't perfect squares, but now everything here is a perfect square. So the square root of 16 is 4. Square root of y to the 8th is y to the 4th. There's nothing left behind. We were able to do the math function of square rooting. Okie dokie, artichoke. Everyone's happy? All right. Will you please turn to page 137 of your books? All right. So this is called rationalizing the denominator. So let's do, hey, what is root 11 times root 11? Just 11, right? And what's root 6 times root 6? Just 6. And what's root 157 times root 157? 157. What's root xy times root xy? Xy. Oh, do you understand why those are working that way? Does that make sense? So there's no reason to multiply 157 times 157 and then say, oh, I'm going to take the square root of it. If I'm taking the same number, the same radical times the exact same radical, that means the radical is going to cancel out. It would give it there. Okay? Everyone's good so far? So you're seeing the patterns well. I like it. Okay? So there is a rule in math, and this rule only kind of sometimes takes place in math, sometimes, not always. Okay? And it's called rationalizing the denominator. Now, I kid you not, the only reason why we rationalize the denominator is you realize a fraction is a division problem. Everyone get that? So if I had 3 over 4 and I made 3 over 4 into a division problem, I'd go 4 into 3.00. And if you multiply it out, you'd wind up getting 0.75. Okay? Which means if I took 1 over root 3 and I went to divide it, I'd go root 3 into 1. And that was harder to do by hand. But we have a lot of technology these days. And I imagine there's going to get to a point where rationalizing a denominator is not needed. Okay? It is used a lot in a class called trigonometry because things cancel out, because you use a lot of different right triangles in trigonometry. And a lot of times this does happen because if it's a right triangle, Pythagorean theorem could be used. But we're not allowed a lot of times not to have a radical in the denominator. Now, I will tell you in the world of science, you can have it all day long. And I get it. It's kind of like, well, why? I get you. I understand the well, why. I get it. It's not a real hard thing to do. It's just I don't want to have a radical sign in the denominator. So what you do with this is you want the denominator to become a perfect square. But if I multiply the bottom by something, I have to multiply the top by something, or the exact same thing, in order to keep it the same. Meaning, if I had 3 over 4, and I multiplied the bottom by 2 and the top by 2, I'd get 6 over 8. 6 over 8 is just the non-reduced version of 3 over 4. Agree? So on this one, what I'm going to do is I'm going to go square root 3 on bottom times square root 3 on top. Okay? So let's do the bottom real quick. If I multiply root 3 times root 3, what do I get? What do I get if I go root 3 times root 3? What do I get? Root 9, and root 9 is what? 3. So I get a 3 on the bottom, and then I go 1 times root 3, and 1 times root 3 is root 3. So now this fraction is the equivalent fraction to 1 over root 3. It's just we don't have a radical in the denominator. Okay, so the main goal with this is I want the denominator, I want to be able to multiply the denominator by another radical. So when I multiply those numbers or letters together, they become, excuse me, they become a perfect square. Okay? Does that seem to make sense? It's not a great deal of work. It's just one of those things. So let's look at this next one. Do you guys have this one? Cool. Just making sure. Sometimes my notes for longer. So with the same thought process that I just did, what do you think I should multiply the top and bottom by?
7.
Close. Root 7. Good. Root 7. So multiply the top and bottom by root 7 and root 7. Okay? Hey, what's root 7 times root 7? Just 7. Okay? And then on top, I get 14 times root 7, which is 14 root 7. Now, the trickery now is on this. The 14 and on the top and the 7 on the bottom are not part of a radical. Do you agree? There's not a square root over the 14 or a square root over the 7 on the bottom. So I can reduce this. Reduce. Okay? So 7 goes into 14 twice. So this comes out to 2 root 7. And it's done. So if the outsides reduce nicely, do it. If they don't reduce, just leave it. If it was like 2 root 7 over 3, leave it as 2 root 7 over 3. But if you can reduce it, reduce it. Okay? May I move on? Almost done. You guys have, what, 4 more problems to do? Okay. Talk to me. So root 2 on bottom and root 2 on top. So on top, I get 4 root 2. On bottom, root 2 times root 2 is 2. Can I reduce it? Yeah. Outside, 2 goes into 4 twice, so I wind up with 2 root 2. And you could put 2 root 2 over 1, or you could just leave it as just 2 root 2. That seems kind of sort of okay. Huh. So now, ooh. I gotta make root 200 a perfect square. Hang on, let me list the perfect squares that we should know how to get to. Oops, I forgot 100. Silly me. So that's basically what we have to go up to. What do you think?
144.
Yeah, well, right now, 200's down here, right? Ooh! So we'll take in what we had learned a little bit the other day. And I know that I could do this. Okay. Okay. So I'm not rationalizing it yet. So what's the perfect square on the bottom? Yeah, I'm going to get a 10 on the bottom, right? Because this is my perfect square right here. So I'm going to get 5 over 10 root 2. Okay. We could think about reducing right now. What's going to reduce if we reduce? Yeah, the 10 and the 5. That becomes a 2. That becomes a 1. So I get 1 over 2 root 2. Okay, now we can rationalize. What should I multiply top and bottom by? Close?
1.
No? Root 2. Root 2 and root 2 on top and bottom. So 1 times root 2 is just root 2. And then I have this original 2 that comes over here. What is root 2 times root 2? Root 4 is what?
6.
Root 4 is what?
3. Wait.
Square root of 4. 2.
Oh,
Thought I had you all the way. All right, so root 2 over 4. This is the reduced version. Root 2 over 4 is the exact same number as 5 over root 200. It's just it breaks down a little bit. So sometimes I might incorporate a little bit extra, especially when you're talking about a big radical downstairs. So like maybe make a note, look for perfect square. Just because what I could have done, and you might not know this, but root 400 is a perfect square. So I could have multiplied top and bottom by root 2 to get root 400. Root 400 is 20, and then reduce that way. But I take it back. Root 400 is not a perfect square. 20 times 20. That might have worked. I don't know. That's 12, 169. No, it wouldn't work. Never mind. I'm being crazy. All right. Is there anything on number 3 that I can reduce? 3 and 2 don't reduce. But a lot of people get caught up saying, well, there's a 3 on top and there's a root 3 on bottom, so theoretically I can reduce. And the answer is incorrect because I can only reduce outside, outside, or inside, inside. Does that make sense when I say outside, outside? And inside, inside, under the radical, under the radical? Okay. So what do you think I should multiply top and bottom by here? Root 3. Okay, so on top, I'm going to get 3 root 3. I'm happy about that. On bottom, the 2 comes along for the ride, and root 3 times root 3 would come out to be what? 3. Because root 3 times root 3 is root 9, square root of 9 is. And then this is going to give me 3 over root 3 over 6. Now let's think about reducing. What's going to reduce? 3 and 6, the outside 3 and the outside 6. So that's going to give me 1 times root 3, which is just root 3, and it's all over 2. Done. So 3 over 2 root 3 is the exact same as root 3 over 2. If you plugged it into a calculator, you can get the same decimal, same irrational decimal. Can we do the last one? We good? Number 4. Talk to me, friends. Yeah, top and bottom by root 2. I like it. Very good. So 2 times root 2 is 2 root 2. I have a 5 down there. Root 2 times root 2 is root 4, which is 2. Now, question for you. Could I reduce these right now?
Yeah.
Sure can. They're all outside. Agree? That might save you a little bit. Or if you didn't do that, then this could have become this. And then you reduce. Which way is the right way? Whichever way you see it best. It's all the same. Cool. Ooh. Dude, tons of homework tonight. Page 139, 140. 140 is blank. Yeehaw. Yeah. Yeah, what?
Sorry. With the speaker.
What'd you get for number 1?
Root 2 over root 2.
Root 2 over 2.
Oh, root 2 over 2.
Yeah. You're welcome.